So today we're going to finish up this section on optimization. Yes?
Wait, but doesn't this section still not tell us like what is the min and max? It just tells us like if there's a min and max still.
Well, no. At this point, we're pretty good, right? What can we do at this point? If we can do quite a lot, right? We have the first derivative test, right? What is the first derivative? So suppose somebody gives you a function on an interval. Somebody gives you a function on an interval, and it says it's continuous and it's differentiable on the inside. Continuous on the whole thing, and it's differentiable on the inside. So from this bit of information, you know that there is a global max, right? And there exists a global min. Right? So and maybe the first sort of set of steps that we did allow us to find where those things are. Right? So we can find the global max and we can find the global min. If you remember how to do it, you say, well, find the critical points. Find the critical points, right? So the endpoints and the places where the derivative is 0, right? So places where prime doesn't exist, or prime equals 0, right? And those are the only places where max and min can occur. So max and min can only occur there. Okay. Right. Those are the only places where local or global max or min can occur. Okay. And then if you're looking for the global max, it's easy, right? You just evaluate your function. You say, I'm looking for the global max. It must be one of these points. Let's just evaluate the function and see which point gives us the highest value. That will be the global max. The lowest value will be the global min. Okay. Now, what about the other places? Well, those are the places for those would be places for the local max and local min, right? And you can check if it's a local max over a local min by using the first derivative test, right? So you'd say, right, at these places, I'm going to look to the left of it, I'm going to look to the right of it, and see if the derivative is if the derivative is positive and then negative. If that happens, then you have a local max. If it's negative and then positive, you have a local min, right? So we're pretty good. We're pretty good at this point. For a function on a closed interval, and then for a function on the whole line, it's a little bit trickier, but still the same thing. You look. In that case, you're not guaranteed a global max or global min, right? So if it's say you have a function that's differentiable on R on the whole line, well then. You don't know if there's a global max or global min. There might not be, right? But you can still play the same game and say, let's find the critical points, right? And that would be, well, here the derivative for our function now in the current setting, then the derivative exists everywhere. So you just look for the derivative is 0, right? And what does that give you? That gives you the only locations. For maxes and mins. So you have a bunch of locations for that maxes and mins could be, the only possible ones. And again, you'd use the first derivative test and say, check it to the left and check it to the right, and see if it'll tell you and that will tell you if it's a local max, or if it's a local min, or if it's neither. Right? So actually, we have a pretty complete system at this point. Yeah, questions?
When we do the first derivative test, do we plug in only numbers where f prime of x equals 0, or can we find numbers where f prime of x does not exist as well?
Where you're doing the first derivative test? So Same thing, right? You could have something like this.
Okay.
Okay.
So
right.
we
And the first, so you have your critical point, right? Here's your critical point. It's a place where the derivative doesn't exist, right? You know that that's a possible location for a min or a max. Right? And so you check the derivative before. Lo and behold, the derivative before is positive and the derivative after is negative. And so that tells you that that point where the derivative didn't exist is actually a local max.
So when we find f prime of x and then we set it to 0, we should also look for where it does not exist.
Yes,
Exactly.
yes. So that's this business of finding the critical points.
Okay. Okay. Thank you.
Okay. Okay. Mariah, you still look kind of skeptical. Why are you skeptical?
No, yeah.
No? Okay. Anybody else want to talk about it?
Are you doing your encouraging things?
I'm trying. Yeah. Yeah. You know, every few years, professors are allowed to go on sabbatical. Basically, it's it depends on the school, but for example, at Scripps, if you, I think maybe you work for 6 years and then you get 1 semester off for free. So I had 1 semester off, 2009, and so during that time I was just doing research, and I didn't need to show any expression on my face or anything like that, or like read other people's expressions. And so that fall when I came back, I was like, oh my gosh, I gotta like sort of loosen up my face or something, because I was just like like this the whole time. I was like, oh. What can I do? I'm gonna have to like be more expressive or something. And so the Newt Kopp, who just retired from Keck Science Biology, he said, I have a suggestion for you. Why don't you use like those tragedy and comedy masks, like from Greek theater? You can just like hold it up. Anytime you need to show your expression, you just have a bunch of masks up there. So that was his suggestion. Okay, so today we're going to be talking about concavity. Something called concavity. Okay, and just to give you a very rough notion of what we mean by concavity, I'm just going to draw some pictures. Okay, this thing here sort of embodies the notion of concave up. This is what we mean by concave up. Something that looks like this. Something like this we call concave down. Now I'd like you to take 1 or 2 minutes and just write down how you would describe this sort of thing mathematically. What can you say about this sort of thing mathematically? Like, how would you describe this using your current vocabulary? What can you say about it? Just make some observations about it, say, using the idea of derivative, say. Okay, just take a minute and see if you can write down anything at all about either one of these. Maybe concave up. And you can talk with each other.
I know. We just got this out of us. God, I love this show. Don't even need to study for the file.
That was on Friday. What?
I know.
No, it's on Friday.
Yeah. I think that this one and I was like, oh,
So we had a nice segment. So. What?
It's scary. We just go into the lesson we were actually taking the class.
We're all.
It's all like,
anyone like to say anything about this graph here? What can you say about how would you describe this sort of this sort of curve using? Yeah, go ahead.
Is it not mathematic enough to say initially decreasing its local min and then increases?
So you could say decreasing, reaches a min, and then increasing. Okay, that's all right. Can anyone let's just throw up a bunch of observations about it. Okay, so certainly that's true. It's decreasing, reaches a min, and then increases. Right. Kimaya, you have the hand up.
Like the slope of the tangent line starts out steep and gets like less and less.
Okay.
Like the derivative, the first derivative like gets smaller as you approach zero, like it's bigger.
Okay, so the slope is pretty negative, right? And then what happens to it?
It goes to zero.
Right, it gets, the slope sort of becomes more gentle, right? So it starts out pretty steep, and then that steepness sort of lowers and goes to zero, right? And then what happens?
And then it like goes back up.
It becomes slightly positive, and then more positive, and then more positive, and then more positive, right? Okay, yeah, so the slope is very negative, then less so, then zero, then slightly positive, then very, very positive. And these are sort of subjective terms. Okay, right. So yeah, so the slope goes through a sort of shift here. Yeah, Sarah.
We could also like express it in like the form of like a double, like a two-sided limit, like as it comes from the right and the left of zero.
So you're saying that, can you say that
Like
again?
the slope, like it's like I think that the slope approaches zero as like you can say like as h approaches like a certain point.
Okay, so you're saying that there's this point here, and the slope, the limit of the slope, say, from the, as x approaches, let's call this point C, say, x approaches C from the left-hand side, well, how do you want to say it? It's zero, right? But what you want to say is that it's sort of approaches zero from the negative side, right? And you also want to say something similar from the other side, right? So I'm not sure how you would say that. Well, you could say this, right? That this is not exactly what you want to say. You want to say something like this: that the slope is negative for x less than c. For x less than c, the slope is negative, and the limit as x approaches c from the left-hand side is zero, right? So it's negative on the left side, and it goes up to zero, right? But does it go up to zero? Okay, and then similarly from the other side. Okay. Let me ask you this: does it change its direction? Does it say does it head towards zero and then go back down again? No. Okay. Other observations? Anything else? Okay, let's look at this one here. Slope is very negative, then less so, then slightly positive, then very positive. Can somebody say that a bit more concisely? Yeah, Megan. Slope is increasing, right? Okay, great. Slope is increasing. Right, slope is increasing. Right.
The slope of the tangent line is increasing?
The slope, yeah, of the tangent line. So maybe say like this: f prime is increasing. Yeah, f prime is increasing. Okay. Could we say that? Can we express that in another way? F prime is increasing. F prime is an increasing function. How do we describe an increasing function? Claire.
F double prime is positive.
F double prime is positive. f double prime, say, is positive, as long as f double prime exists. Okay. So this is the notion of, all these things are, related to what we're saying here. Yeah, Laura.
Do you always like read functions left to right?
Yes, yeah, you do.
Okay.
Yeah, yeah.
Is that just convention?
That's just convention, yeah. And I think I had a left-handed professor in graduate school who said that it always irritated him that the number line was positive on the right and negative on the left. For him, he wanted to read it in the opposite direction. Yeah, so. Okay, so yeah, so that's great. Here's the definition. If you have a differentiable function on AB, we say f is concave up on AB if f prime is increasing. And we say f is concave down if f prime is decreasing. So similarly for concave down. Okay. The pictures are a little bit misleading because you don't have to go through 0. For example, if I just took this right hand side here, this we would also consider to be concave up. Okay. This right portion here is concave up, right? The derivative is positive, and then it becomes more and more positive, right? Or the left hand side here. So it doesn't have to have this full progression. Okay. We have this observation that this connection, right? If f is twice differentiable, say f is twice differentiable on AB. Okay. If f double prime is bigger than 0 on AB, then it's concave up. And if f double prime is less than 0 on AB, then f is concave down. So there's a relation between the second derivative and concavity. If it's positive on the interval, you're concave up. If it's negative on the interval, you're concave down. Okay. So for a simple example, right, if somebody says, let's look at x cubed, right? Then what's the what do we know about its concavity? Well, I'll take half a minute and see what you can say about the concavity, or just look at it. Now you know what it is, right? All right.
Okay, how do you choose the interval AB? Because like the function might be defined on like something larger than AB, right?
Yeah. So here we're on the whole line. Say.
Okay. But like, are you like given AB? Like, why do you decide to look around that interval? Is that where the critical points are?
Hold on.
Okay.
Hold on. So you're wondering. Wait. If you wait for about 5 minutes, then I think all your questions will be answered. Okay, so what do people say? What can you say about concavity? Yes, Sarah.
That it's concave up.
It's concave up. Let's see. The first derivative is 3x squared. Right. First derivative is 3x squared. So and we can go, if we want, we can look at the second derivative. The second derivative is 6x. Okay. So if we look at the second derivative, let's say we look at the second derivative. Second derivative looks like this. So the second derivative is, this is f double prime. The second derivative is positive here. Right? It's positive from 0 to infinity, and it's negative from negative infinity to 0. It goes here. So f cubed, prime, dx squared, double prime, 6x. Right? And right, so f double prime is bigger than 0 on 0 infinity, less than 0 on negative infinity to 0. Right? So do you want to change your answer, Sarah? You
So
wanna change it?
is A, B like the whole number line?
Well, no. No, in this case, we found a place where the first second derivative is positive. 0 infinity.
Yeah.
It's positive there. So that tells us that f is concave up there on 0 infinity. So, right, and then here, this tells us that f is concave down. That's right. So it switches actually. So on half of the line, it's concave down, and on the other half, it's concave up. And if you think about your the graph of x cubed, right, which looks something like this, then maybe that makes sense to you, right? Here, the derivative is decreasing, right? Here, the derivative is decreasing, and then it becomes 0, and then the derivative is increasing. Right, so here it's concave down, here it's concave up. Right, so there's this point where the concavity switches. That point is called a point of inflection. There's a term for that. Point of inflection. Inflection point. It's not that important a term, but yeah, Mariah.
Wait, so the derivative is always increasing, though, right?
Let's-
Or sorry, it's always positive. I mean.
Okay, the derivative is always positive. Yeah, here's what the derivative looks like.
So
Right?
yeah.
The derivative is always positive. That tells us that our function is always increasing. Right?
Okay.
So our original function is always increasing. Yeah, it is always increasing. Okay. But you notice that the derivative, although it's positive, is decreasing here, right? And so decreasing is what we call concave down.
Okay.
Right? The derivative is decreasing here. That's where the function is concave down. The derivative is increasing here. That's where the function is concave up.
Okay. But then the whole function is increasing always.
The whole function is always increasing because the derivative is positive,
Okay.
right?
Mhm.
So you have to sort of keep these ideas separate, right? Increasing and concave are not the same thing, right? Here the function is definitely always increasing, right? But it's concave down here. It's increasing concave down. Here it's increasing concave up.
Okay. When it's going like concave down, it doesn't really get to like the concave down point though, and that's like what's important because then it like switches back up. Does that make sense? Like it doesn't finish the. I don't know if that makes sense. Like
So
it
it
looks
doesn't.
like it gets to 0.
It
and
doesn't. It doesn't go like this.
Yeah.
That's what you're saying. Yeah.
Yeah.
And that's why I said that the pictures that I drew earlier were a little bit misleading because to be
Okay.
concave
Oh,
down,
yeah.
you don't have to go
Okay.
all the way through this thing. You just
Okay.
have to be. Your derivative just has to be decreasing.
Okay. Okay.
Okay. So yeah. It's like where's the concave down, right? But this is actually the concave down. Yeah. Yeah. Claire.
Would the other half of the concave down be if it was decreasing in concave down?
Mhm.
Okay.
Yeah. So if we looked at say negative x cubed,
Mhm.
right? If we looked at negative x cubed, then that function would look like this. It would be a decreasing function that was concave up here and concave down here. Right. Okay. Okay, so so now we're going to go. We're going to tie this notion of concavity with our problem of optimization. Okay. What does this have to do with maxes and mins? What does this have to do with maxes and mins? Do you want to think about that? Think about that. You don't even want to think about it. Think about it. Think about it for a minute. See what you can figure out. What does concavity have to do? What does an increasing derivative have to do with maxes and mins? So I'm going to set it up. Here's the setting. You have a critical point. Or rather, you have a point where, say, f prime is 0. Okay. Say f is concave up everywhere. So the derivative is increasing. Okay. I'll call on you first, Sarah. Talk about it. Talk with each other. Here it is. You have a point where the derivative is 0. Suppose you know that f is concave up. Does that help you? Does it tell you anything about this being a max or a min?
Yes.
Yes.
Didn't tell anything about didn't tell you anything about yes.
Does it mean that the point is a min?
We didn't mean to say f or
F is concave up.
f is a function. Okay.
Yeah.
Yes.
Yeah. Because everything comes from that.
Okay, Sarah, yeah.
I was saying that if you know that it's concave up, then and if the derivative is 0, then you know that it's a local min.
Why do you know it's a min?
Because like the slope of it is increasing from the negative side and then increasing here, so that when the slope is 0, that means that it's like the lowest point on
So let's think for a second. So the derivative is increasing, right? So and you know that the derivative is 0 here, right?
Yeah. Well, if it's concave down and the derivative is 0, isn't that like at the point where when the derivative is changing from negative to, from the having.
Yeah, that's right. That's right. Yeah, that's right. Very good. So wait. Say it one more
I
time.
wasn't saying it very well.
Say it one more time. Say it one more time.
So if you know that the f prime is 0 on concave up,
Yeah.
you know that it's a local min.
Local min, and why?
Because the derivative is increasing, so
Mhm.
that's coming from negative to positive.
That's right. So this is the place where it's switching over from negative to positive, right? If the derivative is increasing, suppose if it's concave up, that means the derivative is increasing. Here the derivative is 0. Well, that means on the left it must be negative, on the right it must be positive, right? So yeah, Victor.
But this would only hold true for when that's entirely concave up, right? Because, like, for example, x cubed wouldn't necessarily be true.
Right. So we'll make this. We'll be more careful about it in a second. But right now, let's suppose your function is concave up everywhere. Okay. Yeah. So does everyone see that? Right. If it's concave up, that means the same thing as saying that f prime is increasing. F prime is increasing. Right. Well, if f prime is increasing, that means that let's call this point C. To the left of C, to the left of C, f prime is negative. Right? And to the right of C, f prime must be positive. Right? Because it's zero there, and it's increasing. So to the left it must be negative, to the right it must be positive. And so that tells you that it was decreasing before and increasing after. And so C is a min. Right? C is a local min. Okay. And similarly, right, if you knew that your function would concave down, then you know it's a local max. Okay. So this is the idea. This is exactly the idea behind the second derivative test. And I should give you at least 1 or maybe 2 points, Sarah, on the final.
So that's the second derivative test?
No, not exactly. But that's the idea. This is the idea. This is the idea. Okay, this is the idea. And let me write it down properly so that we don't have to say too much. We don't want to have to assume that the function is concave up everywhere. All we need is the function is concave up in an interval around that point. So say f is twice differentiable on AB, and let C be a point in AB, and say, suppose f prime of C. Okay. So suppose you have this point where the derivative is 0, right? If f double prime C is bigger than 0, then C is a local min. If f double prime C is less than 0, then C is a local max. If f double prime C equals 0, then then there's no information. And just to make it a little easier to explain, I'm going to throw in a word here. Twice continuously differentiable. So what I mean by that is the second derivative is continuous. That will make it easier to talk about.
And why did we even learn the first one? I feel like this one is much easier.
This one is much easier, but you need to assume more about your function. The first test worked on a function that's 1 time differentiable. And this one you need your function to be 2 times differentiable. So it doesn't work as often.
Okay.
Now you might think
It's
like,
continuous. Like, wouldn't it be 2 times differentiable?
does continuous mean that it's differentiable?
Well, to be differentiable, it has to be continuous.
That's true. Yes.
So, I know, I guess not.
No,
It's
not at all.
differentiable once.
No, not right. You could have a
I can't think of an
function
example.
Hmm?
I can't think of an example.
of a function that's continuous but not differentiable.
Not twice differentiable.
Not twice differentiable. Yeah, that's sort of a hard one to think of. I actually don't have a good example offhand.
Okay.
But it is So yeah, in the 19th century, so it used to be that people thought all functions were continuous and differentiable, like infinitely differentiable. In the 19th century, this guy named Weierstrass, one of the great mathematicians of the later 19th century, came up with a function that was continuous but differentiable nowhere. So it's even easy to come up with a continuous function that's not differentiable at a point. Right? Here's a continuous function; it's not differentiable at a point. But Weierstrass came up with this function that was continuous but differentiable, never differentiable.
What does it look like? Can you draw it?
I can't draw it. It's sort of like a fractal, if you know this. If you know this term, a fractal. Yeah.
Wouldn't it just be a line?
No, that's differentiable everywhere.
Differentiable.
Right. That's right. Remember, differentiable means basically line-like.
Oh.
Right.
Okay.
If you're line, you're differentiable everywhere.
Yeah.
If people thought that you could like differentiate infinitely, like can't you? If you differentiate a couple times, won't you normally get 0? Like
If you're a polynomial.
Oh.
But if, say, you're a sine function, then
Okay.
no matter how many times you differentiate, you do not vanish. Right. Or if you're the exponential function, you don't even change at all. Right?
Yeah.
Yeah, so Weierstrass came up with this function that was nowhere differentiable. Look it up. They probably have something like a picture of it on the internet. It sort of, the older mathematicians, it horrified basically a lot of the mathematical community, but made them aware that they had been oversimplifying their thinking before. Yeah. Okay. So So let's just do an example of this, and then I'll try to. No. Let's explain this. Why does this make sense? Okay. So you have this function at some point f prime of c. It's basically what Sarah said. You have some point c, and you know that the derivative at that point is 0, right? Have c where f prime of c is 0. You know f double prime of c is, so if f double prime of c is bigger than 0, then f prime is increasing around c. Right? There's some, right, if f prime is bigger than 0 there, well, there's some little neighborhood where f prime is increasing. Okay. Now let me say it this way. If f double prime is bigger than 0 somewhere, then f double prime is bigger than 0 around c. So in some c minus delta, c plus delta, okay, in some neighborhood of c. Okay. So that means that f prime is increasing in c minus delta, c plus delta. Okay. And then we just say what Sarah said. If it's increasing and it was 0 there, then it must be negative on the left and positive on the right. Right. So f prime is less than 0 in c minus delta c, and f prime is greater than 0 in c plus delta. Right. On the left-hand side, it must be negative. On the right-hand side, it must be positive. Right. So c is a local min. So this is basically what Sarah said, just in mathematical writing. Okay. So don't be intimidated by the mathematical writing. You understood it before. This is just the same thing. Okay. So if the second derivative is positive, then you know that it's positive nearby. If it's positive in this little neighborhood, so this is because f double prime is continuous. So that means it's increasing in that neighborhood. That means that it's increasing in that neighborhood, right? And that means that, well, as we said before, it's negative before and positive after. So you have a local min. Anybody confused by this? Yeah.
So if the
questions?
f prime is less than 0 and the f prime is greater than 0, those two lines, that's basically taking the first derivative test?
Yeah. So by the first derivative test, C is a local min. Yeah. So you use the first derivative test to get the second derivative test. Right. F prime is negative here, F prime is positive here, and it's 0 at C, so it must be a min. Mariah, you look pained.
Can you explain it again?
Yeah, I'll say it one more time. Okay. So F prime of C is 0. F prime of C is 0. F double prime of C is bigger than 0. F double prime of C being bigger than 0 means that F double prime of C is bigger than 0 somewhere around in this neighborhood here. Is that okay?
Yeah.
Okay. Well then, F prime is increasing in that neighborhood. If F double prime is bigger than 0 here, that means that F prime is increasing. Right? Okay. Well, if F prime is increasing and F prime is 0 here, then it must be negative here and positive here. Because it's 0 in the middle, if it's increasing, it must be less than 0 here and more than 0 here. Right? Because it's in F double prime, because F prime is increasing. Right? So it's F prime is less than 0 here and more than 0 here. So by the first derivative test, that must be a min. Okay. Just think of what we said before, right? You have a point where the derivative is 0. If you know that f prime is increasing, well, that must be negative before and positive after. That's exactly what we're saying here, right? There's a place, you have this neighborhood. It's not the whole line anymore. It's just this little neighborhood. You have a little neighborhood where f double prime is positive, right? So you have this little neighborhood where f prime is increasing, right? And it's 0 in the middle of it, so it must be negative on the left and positive on the right. Same thing. Okay. Yeah, Sarah.
Is the line, would you just like F prime, let's see?
Yeah, that's f prime. Okay. Okay. Anyone confused? Anyone confused? Okay. So let's do. We'll just do a couple. We'll just do maybe one example. So you have this function. F of x is 2x cubed plus 15x squared plus 24x plus 23. Okay. So let's just do it together, right? We want to find, let's find maxes and mins. So take the first derivative, we get 6x squared plus 30x plus 30x plus 24, right? That's 6 x squared plus 5x plus 4, right? That's 6 x plus 4 x plus 1. Okay. So you know that f prime equals 0 at negative 4 and negative 1. Okay. You could use the first derivative test, but let's just pretend let's just ignore the first derivative test and use the second. Okay. Second derivative is 12x plus 30. Right. And this is continuous, so that's good. So let's just evaluate. f double prime of negative 4 is negative 48 plus 30, that's to say negative 18. F double prime at negative 1 is negative 12 plus 30, that's to say positive 18. Right? So this is negative. That tells us that negative 4 is a local max. This tells us that negative 1 is a local min. Okay. Okay. So this is how you use the second derivative test. Any questions? Yeah.
So you're thinking was f prime, double prime, negative, is negative 18, that's negative, so it's a max. It's concave down, so it's a max.
Right. So that's right. It's concave down nearby, so it's got to be a max.
Okay.
Here the guy is concave up, so it must be a min.
Okay.
Right. So you find the critical points first. Find the critical points. And then you check what the concavity is at those critical points. So it's not that wherever the function is, wherever the second derivative is negative, you have a max. It has to be at a critical point.
Right.
Okay, that's it for today. So next time, I should say we're going to skip the next section, which is basically sketching graphs. Which I don't think is all that useful in this day and age. And then we'll go right into L'Hopital's